very good afternoon to everyone and a warm welcome to Mr. Niruj Mohan Ramanujan sir for coming here for the Astronomy Code camp virtually. So the entire idea of this program was to give detailed information and for students to make things accessible on the planetarium YouTube page so that they can maybe later can refer the things and can get the better understanding. So about Mr. Niruj Mohan Ramanujan, I would like to give a very small introduction about sir. He's a formerly at National Center for Radio Astrophysics, TIFR Pune. Mr. Niruj is a radio astronomer by training and previously worked at NCRA Pune and currently at SARAO, South Africa. His research interests are radio interferometry, algorithm and pipeline, and is interested in designing large-scale EPO campaign. He was a co-recipient of first Zubin Kemwani Award for Astronomy Outreach. He is a chairperson of the Outreach Committee of the African Astronomical Society. Planetarium, welcome you, sir. Today we also have Saurabh with us. He did the first introductory session yesterday. So the today entirely he'll be available during the code camp. And all the students are eagerly waiting for you, sir. Please, you can start the presentation. We are live now.
Yeah, thank you so much. Thanks for the introduction. I'm currently working at the Indian Institute of Astrophysics in Bangalore.
Sorry.
I changed the job since you last saw me. Anyway, so can I share my screen needs to be put up?
Yes, sir.
Yeah. Okay. So shall I start then? I'm assuming this is readable. I'll just make the font a bit larger. So what I'm going to do is to use what Saurabh had gone through yesterday, and do a little bit of maths with it, right? So I'm going to basically do Gaussian random distribution for normal distributions and a bit of Fourier transform. And the reason I'm doing these two is because Saurabh is going to use these tomorrow to tell you how to analyze a bit of data from a pulsar taken through an actual telescope. Okay, so I import NumPy as capital N. That's my choice. You can import it as NumPy itself, like yesterday, or as NP or whatever. Right? The matplotlib is the plotting script, and this matplotlib inline is so that I can plot it inside the notebook. I'm also importing PyLab, which is a binding onto matplotlib as PL. So whenever I plot anything, I'll be using PL. So I'll say PL.plot, etc., etc. I'm importing some mathematical functions as M. So for example, square root, sine, cos, tan, etc. would be inside M. Okay, and I'm also importing curve fit in case we need it. I'm not sure if we do. So I'm going to basically use a module in NumPy called random. Okay, so how do I know what all it does? So I can say question mark, and then I run the cell, and then I get something like a man command, right? So let's look at that. So basically n.random, you can create an array of numbers which follow a particular distribution function. Okay, and you can choose which distribution function you want. So for example, you can have distribution functions such as beta, the binomial distribution, chi-square distribution, exponential distribution, the gamma function, hypergeometric, Laplace, etc., log normal. So you can generate a sequence of numbers which follow any of these distributions. Okay, so uniform, normal. We're going to use normal. Normal is the same as Gaussian random, but let's look at uniform first because that's something which you might be familiar with, right? So if I say n.random, n.random, something weird is happening. Random.uniform, right? And then I run this. It says uniform takes three arguments. One is low, one is high, one is size. which basically means that this will create a number of a few numbers. How many numbers? Size numbers. Okay, so size tells you how many numbers or the size of the array created, and it will be uniform, and these numbers will be uniformly distributed between the numbers low and high. Okay, so if low is 0 and high is 1, which is the default, then it will, and size let's say is 10, then it will create 10 numbers which are taken from a uniform distribution function between 0 and 1. Okay, so let's try that. Yeah, uniform. Random dot form of 0 to let's say 10, and I want 100 numbers, right? So this is what it will. So this is an array of 100 numbers which are uniformly distributed between 0 and 10. Okay, so I'm going to call this x. Okay. So what I'm going to do is I'm going to say I can plot x. I can plot each one by a point, and I get a uniform distribution between 0 and 10. The x-axis tells you the 100 numbers, and the y-axis tells you the actual values, right? But then plotting them doesn't give me anything much. So what I'm going to do is I'm going to put a histogram of x instead. So the default number of bins for pl.hist is 10, and I can increase it if I want to. So this is a histogram, and it seems like there's a pattern, but that's not true. It's because of small number statistics. This is actually uniform distribution. And since you will not believe me, I'm going to take 10,000 numbers and then plot the histogram, and you see it's uniform, right? Not only that, I can increase the number of bins. Let's say to 100 bins, so we sample it slightly better, and you can see the distribution is roughly uniform within noise, right? And this is what it does. So it creates 10,000 numbers. This creates 10,000 numbers between 0 and 10, which is taken from a uniform distribution, which means that the probability of finding a number between some value x naught to some other value x1 within 0 and 10 is the same for all x0, all x naught and x1, right? So that's what it means. So in any bin, the probability of finding a given number inside any bin is the same. So it's uniform, right? Now that is what we're going to use is something called normal distribution, and this is something you must be familiar with already in some other context. Normal distribution is basically the term used to describe a Gaussian random distribution, which basically means that if you plot a histogram, then you're going to get a shape which is a Gaussian, right? So and it's taken from there. It also means other things. For example, it's independent, identically distributed, and so on, which I won't go into now because I'm assuming you have some idea as to what a random normal distribution is, and we will just go ahead and create some. So again, from low to high and the size, right? So I'm going to create 10,000. Okay, and I'm going to now plot the histogram, and you'll see that the histogram of this looks like a Gaussian, and as expected, the mean is roughly 0, and the dispersion is we are given the dispersion as 100, and that's basically what you see here, right? How do you know dispersion is 100? I can now calculate the standard deviation of x, and that will give me roughly 100 within some error. And what this error is, we will see as we go along, right? So this random dot normal creates 10,000 numbers which have mean 0 and have a standard deviation of 100. Okay, I can now change it. Let's say I want mean 0, standard deviation of 1. Okay, and then I get the standard deviation is roughly 1, right? Let me also plot the mean. So mean is roughly 0, it's minus 0.004, and the standard deviation is roughly 1, is 1.009, right? And if I plot the distribution function for this series, you'll get the y-axis, the x-axis instead of going from minus few hundred to few hundred, now goes from minus a few to few, right? And roughly this much is 1. The sigma is 1, basically means that this is basically the RMS deviation, right? And 2.3 times this is the FWHM, and that's something you can also verify, right? So So this we now know creates a normal distribution. And what are the features of this? So we know that a Gaussian distribution or normal distribution, it's specified purely by basically its mean and standard deviation. All other higher moments are functions of the standard deviation only, and therefore if I increase the second number, which is the standard deviation, then this broadens out, right? And if I change the mean, then the average value changes. So for example, if I change the mean to 10, then the center of this distribution is 10. Okay, so the mean changes the center of this distribution, and the sigma changes how wide or broad the distribution is around the mean. And as you can see, if you have less number of points, you're going to have more error, right, as expected. So the distribution is not going to be looking very Gaussian, and the more the number of points, the more you're going to approximate the perfect Gaussian distribution, right? So now it looks very, very nice, right? There's still some amount of asymmetry at the top, you can see, and that's again because we don't have enough numbers. But then as you increase the number, and we'll see this below, you're going to get better and better approximations of the Gaussian. Here is almost perfect. This is like some textbook version of the Gaussian. Okay. So what we're going to do now is do this a bit properly. So I showed you. So now we're going to do it properly. So I want to have a Gaussian distribution of RMS, let's say 1, and then 2, and then 3, 4, and see how they differ. Right? We already seen how they differ, but let's plot it and see. Okay. So what I've done is RMS is a list which takes the values 1, 2, and 4, and these are the values I'm assigning the RMS, right, or the standard deviation, and I'm going to open a figure. Fixed size is 12 and 8, basically means that in the x-axis it's 12 and the y-axis is 8 units long. So it creates a rectangular box, which is more like landscape. And then I'm going to loop over the RMS, right? So for I in range of 3 as in, I'm going to take I is going to be first 1, then I is going to be 0, 1, 2, and I'm going to use the RMS values for those. I say I generate a random variable x which has 1000 points, right? Has mean 0, and it has RMS of I. So RMS of I is going to take the values 1, 2, 4 for I equals 0, 1, 2, right? Remember, Python, the index starts from 0, right? So the first time I run this, I'm going to generate 1000 numbers with RMS 1. Second time I run this, I'm going to generate 1000 numbers with RMS 2. The third time I'm going to generate 1000 numbers with RMS 4. Okay, and I'm going to make a subplot. So I'm going to make a plot of 4 in the four rows and 1 column, and I can index them as I plus 1. The reason I'm saying I plus 1 is because subplot indexes go from 1 and not from 0. And since range goes from 0, I add 1 to it to give me the plot number. So as I goes from 0, 1, 2, 3, 0, 1, 2, then it goes from, this goes with plus 1. Okay. Now, and then I'm going to plot x, right? And I'm going to adjust the scale so that the y-axis is always minus 16 to 16. Okay. And I'm going to add a string at the end. So this is what I'm going to do. So, okay, this is why I was confused. Sorry, this is 3. So what I get is this. So if RMS is 1, mean 0, this is the random variable x. Now, of course, because this is Gaussian random variable, the value of x, let's say in the ith number, which is let's say a 400th number, does not depend on the value of x, which comes before it, right? Well, of course, after it. So they're independent numbers, and they're identically distributed because all of them come from the same distribution function, which is a Gaussian with mean 0, RMS 1. Okay, and you can see mean is roughly 0, RMS is 1. Now the same y-axis, I plot RMS 2, RMS 4, and you can clearly make out that the dispersion is more. So the deviation from mean is more, and if you calculate the standard deviation by saying numpy.std, you will actually recover these numbers, which we'll do now and see. Okay. So as RMS increases or standard deviation increases, you see that the deviation from peak to peak, right? How spread out are the values also increases. So what I'm going to do is I'm going to now say, okay, I want to print the value of the mean and the standard deviation just to check what we have. Okay. So this is what I get. For the first one, when RMS is 1, I get mean minus 0.03 and 1.009, which is reasonably close to 1. When RMS is 2, I get 2.113, which is okay, and RMS is 4, I get 4.084, right? And the reason it's not exactly 1, 2, or 4, but differs quite a lot by a few percent, is because I've only taken 1,000 numbers, right? So if I take, and the more the numbers I take, the closer it will just get, will the calculated RMS get to the real RMS. So I'm going to say, okay, 100,000, okay? And I'm going to plot the same thing. Now let's see. Now if you see, now of course I'm plotting a lot more numbers, so it's all one on top of each other. But if you look at the RMS, you can see that now it's closer to the real ones, right? So it's 1.0007, 2.002, 3.9996, right? So the calculated standard deviation of the distribution is actually, it's getting closer to the expected value if you increase the total number as expected. Okay, so this basically, so remember, this is the uniform distribution we saw was like this. So if you look at the distribution, if you plot it, you won't see much difference, right? This is a uniform distribution, all 100,000 numbers uniformly distributed. Now this is, 100,000 numbers with random Gaussian distribution. Looking at them, you can't figure out that they are same or different or whatever, right? Because looking at them, you can't really make out much. What will tell you the nature of the random variable is the histogram, right? So if I therefore plot histogram of this, then sorry, what happened? For the histogram of the uniform distribution, sorry, why am I getting Gaussian? Oh, sorry, I changed it and I didn't notice it. My mistake. Sorry, what's happening? Yeah, so uniform distribution, you do get to see a uniform thing, right? So if I for example plot, if you look at the values, you're going to get all very similar values here, right? So 10,000, 10,000, 9,800, 10,039, 9,942, and so on, right? So the histogram is a uniform distribution. Basically means you're going to get a rectangle. Whereas if you have x as a random Gaussian random variable, if you plot all the points, they kind of look the same as before. But then the histogram will show you that it's a Gaussian random variable. Okay. So now what I'm going to do is the same thing as before. So here I have created x with varying RMSs 1, 2, and 4, and I plotted the actual values. What I'm going to now do is to plot the histograms of all of these three. Okay. So I'm plotting a new one. RMS I'm taking as 1 now. Let's see. Okay. So RMS is 1. And I'm going to define a variable called PW or power as 3 plus I, where I goes from 0 to 2. So I is 0, 1, 2, and the power is going to be 3, 4, 5. And why I'm doing that, we'll see next. Okay. So I'm creating a random variable x, which is random.normal. So I know it's Gaussian random variable. Its mean is 0. RMS is 1. Okay. And the number of data points I'm generating is going to be different. So it's going to be 10 power PW. POW is the power. So it's going to take 10 power PW. Since PW takes the values 3, 4, and 5, I'm going to now successively create 1,000 numbers, 10,000 numbers, and 100,000 numbers. Okay. And I'm going to now plot them. 1 is the number of rows, 3 is the number of columns, I is 0, 1, 2. Therefore, I plus 1 is 1, 2, 3. And I'm going to plot the histogram of this x with 50 bins, and I'm going to title them with the number of samples I have. And I'm going to print out the mean and the standard deviation. Okay. So what do you see now? For 1,000 samples, which is PW equals 3 or I equal to 0, the mean is 0.02 and the standard deviation is 0.966, right? 10,000 samples, it's much closer to 1. 100,000 also is very much closer to 1. Now, remember, this is a random variable. So if I run it again, I'm going to get slightly different numbers. Okay. So if every time you run it, it's going to produce a new set of random numbers. That's why it's random. because seed also varies, and you're going to get different values. So now it's 0.9849, 1.0007, 1.0031, and next time you run it, it's going to be something else. Okay, so and because every time you run it, you're creating a new set of random variables, and you can make out here, as we increase the number of samples, this approximates a Gaussian more and more and more, as you expect. And for 100,000 samples, it pretty much looks like an exact Gaussian, right? And the mean continues to be 0 and goes nearer and nearer to 0 as you increase the number of samples, and the standard deviation goes nearer and nearer 1 as you increase the samples. Okay. Now what we're going to do is to quantify these values. So for different samples, I'm getting different means of standard deviation. We know that as we increase the number of samples, the mean and standard deviation approach the actual value closer and closer. Okay. Now, therefore, let's look at that a bit carefully. Again, I'm going to assume you know some concepts about random distributions already, Gaussian random distributions. So what I'm going to do now, though I will go through it again, I will take 1,000 numbers. Right? So I'm going to generate 1,000 numbers. The RMS is going to be 2, okay, and the mean is going to be 0, and I'm creating. I'm sorry. We're going to create 10,000 numbers, but we're going to do it 1,000 times. Okay, I'm sorry. So we're going to create 10,000 numbers with RMS 2 and mean 0, and we're going to do it 1,000 times. So we're going to have 1,000 sets of x's, each x being 10,000 random numbers. Okay. So, and then I'm going to store the means and RMS of each of these 1,000 x's into these arrays called means and STDs. Okay. So n.zeros.num will create a numpy array which is 1,000 length and filled with zeros and so on, right? So now I'm going to go from I is range of num. So I is going to go from 0 to 999. And for each of the 1,000 times, I'm going to create an x, which is a random Gaussian random variable, which has 10,000 values with RMS equals 2 and mean equal to 0. Okay. And for each of these x's, I'm going to store the mean and RMS into these arrays, right? So after I do it num times or 1,000 times, the means is going to store all the 1,000 means of all the x's, and the STDS is going to store the 1,000 RMSs of all the x's. Okay. And what I'm going to do now is to plot the histogram of the means of the Gaussian random variable and the STDs of the Gaussian random variable, right? So this is what I get. Okay. So as you expect, so if you generate one x, which is 10,000 numbers, you expect the mean to be 0, RMS to be 2, right? But almost, not exactly, but almost. And therefore, if you generate it 1,000 times, you expect all the means to be means of the random variables to be clustered around 0, and you expect all the standard deviations of the random variable x to be clustered around 2, right? And that's exactly what we see. So the mean, so each number here, the histogram plots 1,000 numbers, and each of them is the mean of the array x, which has 10,000 random variables. Remember, okay, and that's clustered around 0, and it goes from minus 0.05 to plus 0.05 roughly, which is quite good, right? And the standard deviations are clustered around 2 as expected, and they go from 1.96 to 2.04, which is pretty good. And these numbers are the standard deviations of the Gaussian random variable x, which has 10,000 numbers in it each time. Okay, so I do it 1,000 times, and then I calculate the standard deviation over those 1,000, right? And therefore, and then I have these distribution functions on the distribution functions, right? So this is the mean and standard deviations distribution function of the Gaussian random distribution functions. Therefore, it's a bit more complicated, right? And I'm going to now I know exactly what they're supposed to be. So if I take the RMS, the calculated RMS of the means is 0.0209. Okay, so if I calculate the dispersion of this first histogram, which is the means of the distribution, that is 0.0209, and the RMSs of the RMSs are 0.0139. Okay, and you know, for a Gaussian variable, you know exactly what to expect. You know that the expected RMS of the mean is basically the RMS divided by the square root of numbers, right? And so therefore 10,000, each x has 10,000 numbers, and the RMS is 2. So 2 by root of 10,000 is the expected RMS of the mean. Okay, so the mean will have an error of 2 by square root of 10,000, which then tells you the dispersion here. So let's say minus 0.05 to 0.05. Let's say the full width half maximum. So that basically by 5 is roughly the RMS. So 0.01 or 0.015 I expect to be the RMS, and I'm getting it as 0.02, which is kind of roughly same, right? And what I expect from the data is 0.02 exactly, and I'm getting 0.0209. Okay, same way I can calculate the RMS of the RMSs. So for each x, I calculate the RMS, and I can see how the RMS of each x is deviating from the mean. So the RMS of the RMSs, that is given by the RMS by square root of 1 over 2 times the total number, which is 10,000. Okay, and that's what I given here. And therefore, you plug that in and calculate, that comes to 0.0141, which is very, very close to 0.0139. Okay, and the reason I've done this exercise to show you that that we have these formulas to calculate, let's say, the distribution functions and the distribution function of moments around the distribution functions and so on endlessly. But you can also verify it yourself very easily by just generating random numbers and calculating them yourself, right? So that's fun. So you can use very basic NumPy functions, and you can generate random variables of any distribution function. You can calculate any moment you want to, and you can calculate moments on an ensemble of random variables and so on and so forth. So all of this is very, very simple to do yourself with NumPy and the Jupyter Notebook. And if you plot them, then you see exactly what is going on. If you plot them, you know that they're Gaussian variable. If you plot the means and the means came out to be uniform distribution, if it was a flat function, then you know something's gone wrong, right? Or if there's some exponential distribution, you know something's gone wrong. You know that the RMS of the means, you know that the means and RMSs are distributed Gaussian themselves, and therefore that's what you expect, right? So that's that. Now the next what I'm going to do is we have taken sometimes 1,000 numbers, 10,000 numbers, and so on and so forth. And let's look at a Gaussian distribution. Okay, let's take the rightmost Gaussian distribution because that's for 100,000 samples, and therefore you get a good statistics. Now the mean is 0 and the RMS is 1. So you see the mean is closer to around 0 and the RMS is roughly here. So it goes to roughly 5, 4, 3 or something, right? So typically for a Gaussian random variable, very, very typically for not too many points, the end to end is roughly 5 times RMS. Okay, very, very roughly. So this is minus 3 to 3, so that's 6. And therefore you get 6 by 5 as RMS, and the actual RMS is 1. So it's not too bad. Okay. So I can ask the question. So this Gaussian random variable is symmetric around 0. So forget the left part. Let's look at the right part alone. Okay. Let's look at only positive values. I can ask how many, if I take 100,000 samples, how many samples will have value greater than 0? That we know is half, 0.5 exactly, right? How many samples will have a value greater than 1? How many will have value greater than 2? How many, let's say, greater than 3, and so on? As you can see, the number of samples greater than 1, 2, 3, etc. keep falling dramatically, right? That's why it's a Gaussian, right? But then you can can you calculate it exactly? The answer is yes, of course. And if you have an RMS, it is 1, so you can express the number of samples you expect more than a value in terms of the RMS. Okay, so RMS is 1. Then I can say the number of samples greater than twice the RMS is this so much, right? Now the point about a Gaussian distribution is that if you look at the fraction of samples more than a given number times the RMS, let's say fraction of samples more than 3 times the RMS, or 2 times the RMS, or n times the RMS, that fraction is the same for all distributions, all realizational distributions, right? That's the property of the Gaussian. And how do you calculate that? That's given by what is called the error function, which you might or might not have encountered. If you haven't encountered it, you can look it up. So error function, which is your ERFC, the conjugate error function, tells you what fraction of the number of samples n are greater than a particular value expressed as expressed in terms of RMS. So if I say how many more than 3 times RMS, 4 times RMS, 5 times RMS, this will tell you exactly, right? So what is this? So what I'm going to do is I'm going to choose NN as 100,000. So I'm going to have 100,000 numbers, and I'm going to do it 100 times, right? So I'm going to generate 100,000 numbers 100 times. That's I, 100, goes from 0 to 99. And for each I, I'm going to generate X, which is a random variable, mean 0, RMS 1, and 10,000, 100,000 numbers, right? And I'm going to define a variable called NSN, which is an empty list. I don't know if have you encountered an empty list yesterday, but there's an empty list with no elements right now. And I'm going to take 6 values, right? So I'm going to take the value 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. And I'm going to say, I'm going to calculate the number of samples greater than J times J. Okay, so now actually it's J times the RMS, which is 1. But since RMS, so let me make it a bit clearer. That's clear. So what I'm doing now is that I'm going to calculate. Let's look at this. The where function. I don't know if it was we went through where function yesterday. Where function will do exactly pretty much what you expect to do based on the English on the code, right? X is a NumPy array which has 100,000 numbers, and I said X greater than J times RMS. RMS is 1. The first time J is 0. Therefore, J times RMS is 0. So I'm going to say, where is X greater than 0? Okay. So wherever X is greater than 0, those indices you give me. Okay. So you're going to give me all the indices where X is greater than 0. So if the mean is 0, therefore the number of samples where X is greater than 0 is exactly half of 100,000, is 50,000. Then it will give me the 50,000 indices where the X happens to be more than 0, right? And I'm going to calculate the number of such values, and I'm going to append it to the empty list NSN. Okay. Then second loop, I'm going to say J is 1. So I'm going to say, okay, I'm going to ask where all are X greater than 1 times RMS 1, which is again 1. So I'm going to ask where all is X greater than 1. It will give me all the locations where X is greater than 1. I'm going to find the length, which will tell me the number of such locations where X is greater than 1. And then I'm going to add it to the list NSN, and so on and so forth. So the last J will be 5. So I'm going to say, give me where all the other locations where X is greater than 5 times the RMS. And I'm going to then count the number of such locations, and that will give me the number of locations where X is greater than 5 times sigma, or 5 times the RMS. And I'm going to add that to the list NSN. Okay. And I'm going to then add it to, I'm going to append it to the NS. Now what I'm going to do is I'm going to calculate the expected value and the calculate. So, okay, let me go one by one. So I'm printing now for each of these J's, I'm going to print the actual sigma. Okay. So the actual sigma, okay, let me put this way. The actual number of samples where the number is greater than 0 times sigma is 50,009 for this particular array, and the expected number is given by the error function, and this is formula, you can look it up online, and the expected number is 50,000, which is obvious because 100,000 numbers more than 0 is exactly half 50,000. Okay. And if you look at all the numbers greater than 1 sigma, the actual value I get from this realization is 15,842. What I expect is 15,865. Okay. And as you can see, as you increase the number times sigma, the number of samples expected and also which is really there is going to keep decreasing a lot, right? And so if you ask how many samples are more than 3 times sigma, I expect 134, I get 134, which is pretty good, right? More than 4 times sigma, I expect 3, I get 2, not bad. And more than 5 times sigma, I expect 0 and I get 0. Now, obviously, as you can expect, as you can imagine, if I increase the total number of samples is 100,000 now, I make the 100,000 into, make it, 200,000 or 300,000, these numbers are going to increase, right? So that's clear. Okay. Now what I've shown on the right side here are these numbers as a fraction of 100,000. That's all. Okay. And 1 minus a fraction of 100,000. So basically, it tells me that this tells me the fraction which is left, right? So if I say 50,000 is a number of samples which is greater than 0, then I'm going to say, okay, how many samples are left behind in the positive axis? So then 0 is left behind because everything is greater than 0, right? If I have 15,865 numbers which are greater than 1 sigma, then 50,000 minus 15,865 are the samples between 0 and 1 sigma. And that is 68% of the total number, and so on, right? So I just do, I divide each of these numbers by 50,000, and then I say 1 minus that is the fraction of numbers between 0 and this num, and therefore those are these fractions, and these fractions are universal for Gaussian random variable. That's why I'm doing it, right? So 0 sigma is 0, 1 sigma 68.3, 2 sigma is 95.5, 3 sigma is 99.7, 4 sigma is 99.99. These expressed as fractions are constant for any Gaussian random variable. Okay, so basically what I'm saying is that if you have a Gaussian random variable which has some n numbers in it, okay, then in that n number you can calculate that without calculating, without getting the numbers, you can say that the number of samples between minus 1 sigma and 1 sigma is going to be 68.3% of the total number of samples, right? And this is going to be true for any Gaussian random variable which you generate of any number. And of course, the expected value and the actual value will be very close to each other. And the more the total number, the closer they'll get. Okay. So if I then run this with only 1,000 numbers, okay, as you can see, the total numbers are less. So only 157 numbers are more than 1 sigma, where we expect 158. But then the fraction is still the same, 68.3, which is what we got last time, right? So the fraction is still the same, but the total actual numbers will scale with the total numbers you have, right? So if I want to make the 1,000 into, we made 100,000, I'll make it, one more zero. I'll make it 1 million. Okay, it's going to take a while. Make it 1 million. The actual numbers are again 10 times higher, but the fraction remains the same. So the fraction between minus 1 sigma and 1 sigma is still 68.3. The fraction between minus 2 sigma and 2 sigma is still 95.45. Right? So these numbers are the same, and these come from the Gaussian distribution itself, right? So therefore, if you know that you have n samples, without generating them or doing anything, you can, if I ask you how many samples are there between minus 3.5 sigma and 3.5 sigma, you can calculate that using the error function yourself. And as we have shown here, they match the calculated values pretty well. Okay, and the higher the number of samples you have, the better is the match. So that's basically what I wanted to tell you about Gaussian random variables. Okay, are there any? There's nobody on YouTube. Okay, fantastic. So now let's go on to the next topic. So before I go on to Fourier transforms, I'm going to tell you one thing, which is that we plotted histograms and so on, right? We plotted histograms, we calculated mean, we calculated RMS, but it's always essential that we plot the data. Okay, one thing you have to realize, especially with doing data analysis in astronomy, is that you should always plot the data. Now, to illustrate that, I have taken this famous example called the Anscombe's quartet. So I defined two x-axis arrays, right? X1 is an array which has the elements 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, 5. X4 is an array which just has 8, 8, 8, 8, 8, 8, 8, 19, 8, 8, 8. And Y1 to Y4 are arrays of other numbers. Now, if you look at it carefully, no two arrays are the same. Each array is different from each other. Okay, so I have X1, X4, and Y1, Y2, Y3, Y4. Now I'm going to plot X1 versus Y1, X1 versus Y2, X1 versus Y3, and X4 versus Y4. So X1 is plotted against Y1, Y2, Y3. X4 is plotted against Y4. Okay, and I'm not going to plot it now. What I'm going to do instead is, for every pair, I'm going to calculate the mean, the RMS, the correlation coefficient, and the linear regression, right? So for when I is 0, I get x of 0 and y of 0, which is x1 and y1 here. And therefore, I'm going to plot the mean of x1, the mean of y1, the RMS of x1, the RMS of y1, the correlation coefficient between x1 and y1 after subtracting mean. And if you plot a straight line, if you fit a straight line between x1 and y1, what do you get as the linear regression? Okay, slope and intercept. And I'm going to write down this value. So basically, for x1, the first row is for x1 y1, second row is for x1 y2, third row is for x1 y3, and fourth row is for x4 y4. And look at this, these numbers look very different, but the mean is exactly the same, standard deviation is exactly the same, the mean of x and the mean of y is exactly the same, the standard deviation of y is exactly the same, the correlation coefficient is almost the same to third decimal place, and the slope and intercept of a straight line fit is almost the same to the third decimal place. This is fantastic. It sounds weird, right? So you have these arrays which look very different from each other, and then you get the same mean of x, mean of y, RMS of x, RMS of y, cross correlation coefficient, and the regression line. And therefore, you expect that these points, though they look different to the eye, are basically roughly the same, right? So they all lie very close to each other, which is why this is true. Which is what you would expect, which is what you would guess, and then you'd go away and do something else. Except that if you plot these points, what you get are four very different distributions. Okay, so and these numbers have been chosen very, very carefully by Anscombe, such that though they are very different points, though they plot very differently, the statistics are exactly the same. And you can always do that, right? For example, you can a much better version of this is now available called the Datasaurus. So please Google for Datasaurus and you'll get something very interesting. So the model of the story is please always plot. Okay, right. So now with that lesson, I'm going to move on to Fourier transforms. I'm going to assume again that you know what Fourier transforms are. Okay, if you don't, then you should read up a bit, and then I'll take it off from there. Okay. Now let's look at what this does. This function called plot. I have defined a function called plot. Okay, it takes array y and the string title. Forget title, doesn't matter. Okay, it plots y. Okay, it generates a 2 by 2 plot. So 4 subplots it generates. And the first one, the first plot on the top left, it plots the input array y, okay, with dots and by joining the dots. Now numpy.fft is the FFT routine in numpy. Same way SciPy has a FFT routine, but we will use the numpy FFT routine. So I'm redefining numpy.fft as FFT itself, so I can use it because there's n.fft.fft.fft and gets very cumbersome. So I will redefine n.fft as FFT. That's all. Okay. Now, how do you calculate the FFT of y? You do that by saying FFT.FFT of y. Remember, FFT, this FFT is n.FFT. So this is n.FFT.FFT of y. But then to make it simple, we are renaming it FFT. Okay. So after I confused you enough, so Fy is the FFT of y. That's all you need to know. Okay. And remember, even if y is real, the FFT of y is complex. Okay, in general, unless y is symmetric. So and so Fy is FFT of y. And now, what is the frequency axis, right? So y is, so the conjugate axis for the y, let's say y is in terms of index. Let's say time series. Okay, let's say y is a time series. Therefore, the values for which you have y are in time 1, 2, 3, 4, 5, 6, etc. Therefore, the Fourier conjugate is going to be of time frequency, right? So we generically call it frequency. So what are the corresponding frequencies? The corresponding frequencies are given by FFT.FFT freak. And you just need to know the length of the array y, right? So once you know the length of the array y, let's say y has 1024 numbers, then length of y is 1024. And if you know that the input array is 1024 times, for example, then you can calculate the corresponding frequency exactly because they go as 1 over time, right? And there's some pi, 2 pi, etc. somewhere around this. So FF is the Fourier frequencies corresponding to the input, right? So input X, let's say, is 0, 1, 2, 3, 4, 5, etc. up to 1023. And the Y is some array we have, which is the data. Then Fy will have the complex Fourier transform of Y. And FF will have the complex Fourier transform of X-axis, of the X-axis, input X-axis. Okay. So if X-axis is time, then FF will be the frequency. And so on. If X-axis is frequency, FF will be time, and vice versa, right? Obviously. Now, the thing about FFT is that the way it's computed very fast is such that you don't get the arrays in the correct order. Okay, let me put it this way. So basically, you're going to have, let's say, input array is 64. Okay, so it's going to divide. The output is going to also have 64 numbers, right? The FFT output will be 64 numbers, but these 64 are arranged in a weird fashion. Okay, it's going to take the first 32 numbers, okay, and let's call it y1, and the second 32 numbers of the output, which is called, let's say, y2, is going to flip y1, flip y2, and then put them together and give it to you. Okay, it's a very strange thing, but that's what it does. So now what you have to do is to flip it back and put it back together. So basically it's going to have 32, 31, 30, 29, 28, 27, etc. up to 1. And then it's going to have 64, 63, 62, etc. up to 33. So that's the order in which it comes. Okay, so it's flipped. So it divided into two halves. Each half is flipped. So you have to unflip it. Unflipping is done by this thing called FFT.FFT shift. And since all this is complicated, is why I'm putting it in one function. So I can just keep calling it and not bother. Okay. So therefore the actual frequency is not FF, but the shifted FF. The actual Fourier transform is not FY, but the shifted FY. Okay. So FFT shift of FY is the actual Fourier transform. I'm going to take the absolute value as the amplitude, the real value as the real, the imaginary value as imaginary, and since for very small numbers you get random, you get any number. I'm going to regularize them by saying if it's less than 10 power minus 8, which is the floating point accuracy, I'm going to put them as 0. If you don't understand why, just ignore it. It's okay. And the phase is going to be tan inverse imaginary by real. Okay. And I'm converting to degrees. So basically, I'm taking y, I'm taking the Fourier transform, I'm then shifting it and switching it to give me, and then I'm taking I calculate the amplitude and the phase this way. Okay. So you can look at this in more detail later, but I'm calculating the amplitude and phase of the Fourier transform of y. That's all you need to know. And the Fourier conjugate of the x-axis is nu, which is the frequency. Okay. So now the second subplot, I'm going to plot amplitude versus frequency. The third plot, I'm going to plot phase versus frequency. And the fourth plot, I'm going to plot the inverse Fourier transform of the Fourier transform of y. And I'm hoping I'll get back the input y itself, right? So Fy is the Fourier transform. IFFT is the inverse Fourier transform. Okay, so the exponential will have a negative sign. And then I calculate the real number. Okay, so basically, this is real because, a complex number is basically floating point 0, and therefore I take the real number. So basically what I'm doing for 2 to 4 is I'm calculating the inverse Fourier transform of the Fourier transform of y. Therefore I expect to get y back. And the point is to see if it does. Okay. So now what I'm going to do is I'm going to take a cos and a sine function. As you might expect, since the basis vectors of the Fourier transform are cos and sine, I'm going to get a delta function, right, in principle, as the Fourier transform. So what I've done is I've taken 0 to 128, but every 0.01. So I have 128 times 100 numbers in x goes from 0 to 128 to 12,800 minus 1. So it goes from 0 to 12,799. And I'm going to define FF as 1 by 16. So I'm going to define a frequency of the sine wave as 1 over 16 in this units. Okay. So input frequency would be 1 over 16. And I'm going to then create a sine function, which is 2 pi x by 16, right? So 2 pi x times frequency. Okay. So 2 pi nu times x, where x goes from 0 to 128 times 100. That's all, right? I'm going to create, and I'm also going to plot it. I'm going to create a cos function. I'm going to plot. Let's see what it is. So look at the top left plot. This is the sine plot. As you can expect, this is a sine function. Okay, nice sine function. And it goes from 0 to 12,800. And this starts at 0, etc., etc. And it goes and goes. This is a sine function. Now the second plot I'm plotting is the amplitude. Okay. So I'm plotting the amplitude of this Fourier transform of the sine function. And this is actually very, very small. You can't see it here. Then you get a delta function. Okay. Which is at 1 over 16. And similarly, you'll get a phase, which is since sine function is it's not a symmetric function, but an anti-symmetric function, you're going to get a one phase going up, one phase which is 90, other is minus 90. And the inverse Fourier transform, as you can see, is exactly the input function back. Okay. Now, again, for cos function, you get the same thing again. You're going to get the amplitude, which is the DC of this. And I'm going to get the phase which is 0 because cos function is symmetric, phase is 0. And I'm going to get and I'm going to get the amplitude, which gives you the total if you integrate over that thing. And without normalization, if I normalize it by the total number of samples, then I will get exactly 1, but I haven't done that. Remember the 12,800 samples, and the inverse Fourier transform of the Fourier transform, I get the original value back. Okay, is what I expect. Now, right. Now what I'm going to do, therefore, once we know that, so we don't know that the IFFT of the IFFT is the original function, I can calculate the amplitude and the phase. And for a anti-symmetric function, you have the amplitude, which is positive, of course, always, but the phase you get negative and positive. Whereas for a symmetric function, you get phase 0, as you expect, and the amplitude is the amplitude, which is not normalized to the sample number. Okay. Now, what I'm going to do is I'm going to generate 3 sinusoid functions. Okay, so I'm going to have the length of the vector as 1024. Okay, so I'm going to create an x-axis, which is 0 to 1023. I'm going to create forget times 1. Let's look at times. Okay, I'm going to have 3 frequencies. One is 1/16, one is 1/32, other is 1/128. Okay, and times 1 is 3 other sets. Forget that. Okay. Now I'm going to say, therefore, input frequencies are 1/16, 1/32, 1/128, which is what these are. I'm going to define sine and cos as func. So func 0 is sine, func 1 is cos. Okay, I'm creating a 0 function. What I'm going to do is I'm going to have 3 functions, 3 arrays. The 0th array has an amplitude I. So each array is going to have amplitude I plus 1, right? So its amplitude is going to be, so when I goes from 0, 1, 2, the amp will be 1, 2, 3. Okay. And it's going to be functions of I percentage 2. I percentage 2 is modulus. Okay. So I is 0, 1, 2. The I percentage 2 is going to be 0, 1, 0. Therefore, I'm going to have first sine, then cos, then sine. Okay. And I'm going to have 2 pi nu x, right? Where x goes from 0 to 1023. So basically, I'm going to have first function is going to be 1 times sine of this. Second function is going to be 2 times cos of this. Third function is going to be 3 times sine of this again. So I just chose it. You could choose anything else. And I'm going to add them all to each other, right? So I'm going to add this, the first function plus second function plus third function, put it into y, right? Y plus equal to z means every time you add the z to y, okay, and to the previous y. And I'm going to plot it. I'm going to plot this function. Now, obviously, this function is going to be a summation of our 3 sinusoids, and therefore, if you look at the black plot, the dark black plot, that is the sum of the 3 sinusoids. The 3 sinusoids themselves are given by the green, orange, and blue plots. So if I add the green, orange, and blue, which is Z1, Z2, Z3, I get Y, which is the black plot, which has this obvious. Obviously, the 3 sinusoids, right? So you see this kind of a repeating periodic pattern. Okay. Now what I'm going to do is I'm going to calculate the Fourier transform of the z, which is of this y, which is the sum of 3 sinusoids, and I'm going to plot those 4 plots again. Okay. Now let's see. So what I get is this. So this top left plot is same as this black curve here. Okay. Now amplitude, instead of having one non-zero amplitude, I have 3. Right? I mean, if you remember, this is symmetric, right? So if you look at the positive frequencies, I have 3 values of frequencies for which the amplitude is non-zero. Okay, and that is not surprising because the input is 3 sinusoids, and we know that's what a Fourier transform does. So we have 3 input sinusoids, and the Fourier transform is giving you 3 frequencies where the amplitude is non-zero. Okay, and it seems perfect. Now, if you remember, the amplitudes were 1, 2, and 3. As the frequency was 16, 32, and 128. So as the frequency decrease, the amplitude increases. And that's exactly what you see here. As the frequency increases, amplitude decreases in exactly 1, 2, 3 ratio. That's all. So you see that's fine too. And the phases are strange, right? Phases, you expect to see six spikes. You see only 4. That's because, remember, we have 1 sine and 2 cos. No. Yeah, sorry. Here 2 sines and 1 cos. The cos function in this plot will have 0 phase. The 2 sine functions will have 2 non-zero phases, which is minus 90 plus 90. And therefore, these 4 or 2 pairs represent the 2 sine functions. The cos function phase is just 0. Okay. Now, if I take inverse Fourier transform of the Fourier transform, I get the original signal back here. Okay, that's the fourth plot. So everything is fine. Now what I'm going to do is I'm going to blow this up. So I here see that I have 6 spikes, but the negative frequencies I can ignore. Positive frequencies, I have 3 spikes for the 3 sinusoids. I'm going to zoom in. I'm going to zoom into this bit, and this is what I get. Okay, if I zoom into this bit, I have these values, and the x-axis where you have non-zero amplitudes are going to be the frequency, which is 1 over the times, right? And that's what you get. Now frequencies you get, so input frequencies are 0.0625, 0.03125, 0.07825, which is what you get from 1 over the times, and if I say, okay, show me all the frequencies where the amplitude is greater than 200, right? This is 200. 200 is this line here, and I say, okay, show me all the points where it's more than 200. I get these values, which are exactly the same as these values, right? So I get back the I get back the frequency of the input sinusoid in my Fourier transform. But look at this. So but the number of points for which the amplitude is non-zero is just 1 per frequency, right? So it's exactly 0, and then just for the correct frequency it goes to some high value, and then the next frequency it goes to 0, right? So, and this is exactly what you would expect. We're saying, okay, we put in only 3 frequencies, 3 pure frequencies. Therefore, we only expect 3 points in the frequency domain where we get non-zero numbers. Everywhere it should be 0 exactly. But that's not true, right? So because remember, your input is only has some length. It's only 1024 long. So that's not really true. The reason I'm going to look at only positive frequencies. The reason only 3 frequencies have non-zero values is not just because I have 3 input sinusoids, but also because the inverse of the frequencies are exact divisors of the total length. Okay, now let's look at that a bit carefully. What do I mean? The total length of the input X array is 1024. Okay, the number of sinusoids I want inside this 1024 are integral to 1024. 16, 32, 128, 1024 is an integer multiple of all of these times, right? If you have integer multiple of all of these times, then you have only 1 point for which the FFT is non-zero. Okay, that corresponds to the exact frequency. And if it's not true, okay, so let's say here, now if you go back to where I said ignore y1. Now let's not ignore y1. Y1 are the frequencies corresponding to times 1. Times 1 you're seeing is 21, 39.5, 103. Now 1024 is not an integral multiple of any of these 3 frequencies, right? And therefore, if you do the entire exercise with these frequencies, with the frequencies which is not, 1 over that is not a multiple, it's not a divisor of 1024, then this is what you get. Okay, so what you get is basically that quite a few points around the correct frequencies, you still get non-zero values. In fact, it goes down quite slowly. Okay, and I'm not going to go into why this is so. Basically, in great detail. Basically, since the input array is finite length, it's like multiplying the infinite input with the box function. The box function's FFT is a sinc function. And what you're seeing, therefore, is the sinc function convolved with the actual input FFT. But then when it's exact integral multiple, you are sampling exactly at the nulls of the sinc function. Therefore, you get only this. And if it's a non-integer multiple, then you sample it in different places. Therefore, you get this. But you can read about it later in your maths textbooks. Okay. So remember that this delta function, almost exact delta function, where the amplitude is non-zero only for the exact frequency, is only true if the total length of the input array is an integer multiple of the number of sinusoids present in it. Okay, otherwise you get this kind of a function which rises sharply and falls sharply, but is non-zero over a range of values. Okay, now so this is something you would use tomorrow when you look at the Vela pulsar data. Now let's add one more thing to it, which again you'll see tomorrow. No real data is like this. All real data have noise attached to it. Now we're going to combine the two things we learned. We learned about Gaussian and noise, and we learned about FFTs. Now we're going to put them together because real data has has noise in it all the time, right? So therefore now let's put some noise into the input. Okay, now what I'm going to do is I'm going to define a 1024 length array. I'm going to have 38 sinusoids and 120 sinusoids in it. So I'm going to have two sinusoids, one with 38 times, other 120 times within the 1024. Therefore, the frequencies are therefore 1 over 38, 1 over 120 in this units. I'm going to then define x-axis like before, and I'm going to have y as this. So my input is going to be sine of 2 pi nu 1 x plus sine of 2 pi nu 2 x. Nu 1 is 1 over 38, nu 2 is 1 over 120. Okay, and since 1024 is not an integer multiple of 38 or 120, you're going to not get a single delta function. You're going to get a rising and a falling function with some non-zero values on either side. Okay, now what I'm going to do is I'm going to create a noise. I'm going to create Gaussian random noise, which is stored in an array called noise. This noise has mean 0, has RMS 3, and has the same size as the y array, which is 1024. Okay, so now I have y, which is the sum of two sinusoids which don't have integer multiple frequencies, and I have the array noise, which is a pure Gaussian random noise with RMS 3, the same size as y. So what I'm going to do, I'm going to plot them and see how they are. Okay, so let's look at. So this is the input sinusoid. Okay, remember the input sinusoid, the amplitudes are 1, right? So the maximum y can go is +2 and minimum is -2, right? And this is what you see here, right? So it goes from -2 to +2. But the RMS of the noise is 3, which means that the RMS amplitude exceeds the input signal itself, which is kind of strange, right? You would expect the noise is less than signal, but we're taking an extreme example where the noise actually is greater than the signal at any given value for the input, right? So the y goes from -2 to 2, but then the noise goes from has a dispersion of 3, which means goes from roughly -15 to +15. Let's say, okay. So noise is many times greater than the input signal. In which case you would expect that the signal is completely lost, which is what you see here. The top plot is the input signal, which is the two sine functions. The second plot is a sine function plus the noise added to it, so it's y plus noise. And as you can see, you cannot make out the sine function here at all. You cannot make out any periodicity at all, and because this noise is much greater than the sine function. Okay. Now what I'm going to do? I'm going to do the same thing as before. So I'm going to now take the FFT. So I'm taking the FFT and I'm plotting the amplitude. Okay, I'm going to plot the amplitude of the FFT of this second signal here where noise is added to it. And what do I find? Now this is magic. What I find are these 4 and therefore these 2 spikes, which seems to be our original signal because we had 2 sinusoids. And these spikes seem to be fairly, easy to spot, right? And the same thing zoomed in is this. Okay. Now input frequency is 0.0263157 and 0.0083333. And the reason they don't, okay, and the frequency is and the highest frequency is 0.02. The SNR is 10.3. That's the point, right? Hold on 1 second. Okay, so I'm gonna do this till I get a good realization. Okay, never mind. So the input frequency is 0.026, 0.0833, right? Now the amplitude has 2 values. So if I zoom in and look at what these values are, these 2 values happen to be 0.0263671.9, and there are 2 values because they're one next to each other, right? So 0.08789 and 0.0078125. And that's because they're close to each other. So you can take the average of it, right? So it says 0.0082 or something, and that's very close to the input frequency, right? So these are extremely close to the input frequency. So I get these back, and the signal noise ratio is 9.7. It's almost 10. So this is the power of Fourier transforms, right? I have a signal which is 2 sinusoids. I drown it in noise completely, but because the Fourier transform is the conjugate domain and all the periodicity is then concentrated into one frequency, I can actually pick out the 2 input frequencies very, very easily at 10 sigma, at 10 signal noise ratio in the FFT, which is fantastic, right? And this is what we're going to do tomorrow. So you're going to take real pulsar data where the pulsar signal can be, can be dominated by the noise, but still, because the signals is repeated over a large number of points, if you're going to look at the signal in the correct way, which is that every time, every winding of the input basis vector, which is sine and cos, you're going to end up picking out the sinusoids with enormous signal noise ratio. Okay, you're going to beat the noise, because remember, I mean, it's not just one peak. You're going to have so many peaks and troughs. You're going to, and in some sense, Fourier transform then takes all of these peaks and troughs and puts that power into one point, and therefore you're going to beat the noise down, and you're going to have high signal noise spikes in the Fourier transform for the frequencies corresponding to the input two sinusoids, right? So this is what you're going to do tomorrow with real data. So I'll stop here. So just to recapitulate, let me recapitulate quickly. So n.numpy.random.uniform of 1, 10, 100, 100,000 or whatever will produce these many numbers with going from 1 to 10 with uniform distribution. Okay, and histogram will be uniform. Random.normal of 3 numbers of 0 RMS of I 100,000 will produce 100,000 points which are Gaussian random distributed with mean 0 and RMS of I, RMS as RMS of I, and therefore higher the RMS, more the spread in the data. And if we plot the histograms of this, it'll then tend towards a Gaussian, okay, whose width is proportional to the RMS and the mean is the same as the mean. Okay, now then we also saw that you also play around with multiple realizations of this ensemble, and if you calculate the RMS of the RMS and RMS of the mean, they actually are very, very close to what you expect from the Gaussian statistics themselves. We also found that the number of samples we expect between some minus n sigma and plus n sigma, which we calculate, is very, very, very close to what we expect, which is given by the error function. Okay, so we saw that as well. And if you change the total number of points, the agreement with what you expect is going to be more and more and more. So everything you learned in theory, you can also do in computation as well. We also learned that you have to plot all the data all the time because data can fool you very easily. Then we looked at Fourier transforms. We saw that the Fourier transform is given by numpy.fft is the main routine, and fft.fft takes a Fourier transform, which is complex in general, and the FFT freak will give you the frequency axis corresponding to the input axis, but then you have to shift and turn these two around, and that's given by the fft.fft shift, and then you get the amplitude and the phase from these. Okay, and if you take a pure sine function, you'll get a single value, which is the frequency corresponding to the sine function, and the amplitude corresponds, of course, to the amplitude of the sine function as well as the total number of points you get. The phase is going to be at the correct frequency. The phase is going to be plus and minus because it's antisymmetric function, and the inverse FFT of the FFT is going to be itself. The cos function is symmetric, therefore you're going to have phase 0, and you're going to have 2 points here which are at positive and negative frequency again, which are at the frequencies corresponding to the input cos, and the IFFT of FFT is the same function again. Okay. Then we also saw that if I add 3 sinusoids and get the black curve, I can then get back the 3 input frequencies in the amplitude of the FFT. Of course, the positive and negative frequencies, and the symmetric ones will not give you a phase. The antisymmetric ones will give you a phase non-zero phase. And if you zoom into the amplitude, you can actually get the exact frequencies which match the input frequencies. Okay. We also saw that the amplitude of the Fourier transform is non-zero for only one point at the correct frequency only if the total length of the array is integral multiple of the input 1 over frequency. If not, then you get a few points around them which will also be non-zero, and this shape is predictable given the input frequency and the total length. This shape is a known shape. Okay, in general, this is what it will be. We also saw that if you add noise which dominates over the signal, FFT, the cool thing about FFT is that you can recover the input frequencies pretty much exactly with high SNR in the Fourier domain. So I will stop there.
That was quite a wonderful session, Professor Niraj. And I don't think that there will be any further questions, but if there are any questions, again, people can put them in the comment box. Maybe we can take a minute or so, maybe if they have any questions, so we can just wait for.
there are none.
Yeah, right now there are none, but still, if there are any questions, you
There are
can
none.
simply
But people who see the video later can add your questions in comments, and I can take a look at it some point later and reply to it.
yeah, definitely, or maybe or maybe they can simply drop an email to the
Yeah, yeah.
planetarium's email, or maybe
Yeah.
to,
So we covered quite a lot of ground today. So hopefully tomorrow's exercise will then use all of this and with real data, right? So that'll be
yeah,
fun.
yeah. Tomorrow will be quite a lot of fun.
Okay, good.
So
Okay, so let's end here.
okay,
Thanks a lot.
yeah.
Thanks a lot for calling me.
Yeah, thanks, Professor Naresh, to for taking this session, and we are gonna end this
I'm not
session.
Professor Dheeraj. I'm just Dheeraj, but thank you nevertheless.
Okay, yeah, okay, no issues.
Okay, bye.
Thank you. Bye bye.